So let's start. So welcome back, and so it's a pleasure to introduce Pierre Le Doussal, which is Director of Research at CNRS at what was the LPT, the Laboratoire de Physique Théorique, which is now just Laboratoire de Physique at École Normale Supérieure in Paris. He made really a lot of great contribution in statistical physics, so he's really a worldwide renowned theoretical physicist in this field. For example, anomalous diffusion in disordered media, or the Bragg glass and the pinning of vortices in superconductors, and then the functional renormalization group, which explained one possible explanation to the avalanches in random freezing model, and last but not least, the KPZ equation. And so he's really the perfect person to speak about this very famous work of Giorgio, and so I'm very glad to let him the word. Thanks.
Thank you very much. It's a great pleasure to celebrate today the famous KPZ paper. On a personal note, I am a little bit too young to know the inside story, although Giorgio told me during the lunch, part of it at least. And in '86, actually, I was doing my PhD in what was at the time LPT UNS with other students like Jean-Philippe Bouchot and Antoine Georges. I think we had one discussion once with Giorgio, but it was something about completely different. It was about generalized Lyapunov exponents. It's only 3 years later that I met Mehran Kardar and David Nelson. And by that time, there was an explosion of activity about directed polymers and KPZ equation. People were very excited about application to vortex lines in superconductors. And these years actually are often called the first KPZ revolution. And since that time, the KPZ equation has been with us, periodically reappearing in various incarnations. What's really in physics and in mathematics, what's really amazing about this work is that it established a bridge between non-equilibrium physics. After all, the KPZ equation is often called the Ising model of the non-equilibrium physics, and other problems such as statistical mechanics of disordered systems. It also established bridges between physics and mathematics, which were very fruitful in recent years. And as you can see from the number of citations, there has been an avalanche of works. And I'm going to focus only on a small fraction of them. I have to apologize, my slides are kind of heavy. There are a lot of formulas. I wanted to reuse them for lectures, but you don't have to read everything on them. I will try to give the main idea. So it is interesting to point out the other important universality class for growth in 2 dimensions, which is diffusion limited aggregation, and this seminal paper, which has roughly the same number of citations. In that problem, one has Brownian particles coming from infinity and sticking to the cluster. So it's a very non-local rule, which leads to branching. By contrast, the KPZ growth has essentially describes any local stochastic rule and leads to much more gentle self-affine interface. Now there are some interpolation between these 2 problems, and these problems are difficult in Euclidean space. So I cannot resist to show very briefly, I'm not going to talk at all about it, but an extension of these problems in fluctuating geometries. And it is called quantum Loevner evolution. It is a generalization of a stochastic Loevner evolution for those of you who know what it is. And connected to quantum Liouville gravity. So it is a conformal growth model which has two parameters, one which is this eta parameter, and the other one which for some value can describe, for instance, the Eden model growth on a fluctuating geometry. So it's something like this. And it's kind of funny that in this field, which is mostly mathematical, the two KPZ, the two famous KPZ can meet. Okay, I'm not going to talk about this. This is the outline of my talk. I will come first to the genesis of KPZ equation, in connection with directed polymer and Berger's equation. Why is it that in one dimension one can find the exact scaling exponents? What is the situation in higher dimension, which is mostly open questions? Then I will come to the second, what's called the second KPZ revolution, which is happened both in math and physics around the year 2000, where exact solution of several discrete models were found and found to exhibit the same universal behavior at large scale, which is called the KPZ class. And at that time, it was possible to compute full distribution of probability of the height field of KPZ. And they unveiled interesting connection, amazing connection actually to random matrix theory and to the so-called Tracy-Widom distributions, which are universal distribution in random matrix theory. Then I will introduce briefly, make some recall briefly about random matrix theory and determinantal process. And then I will move to solution of the KPZ equation using, I will go back to the KPZ equation itself, and its solution using replica. So it's actually possible, and it started around 1990 by works by Cardar and also by Giorgio, but was fulfilled only around 2010. Now, replica, we like them, but they are not necessarily rigorous. So mathematicians actually made them rigorous, and they discovered in the process new mathematical structures, which led to discovery of a pile of solvable models. They showed also some deep but reassuring things, which is like, for instance, that one can actually make sense of the KPZ equation, and that the KPZ equation belongs to its own universality class. Okay. Then I will, if I have time, talk about some interesting property of two-time KPZ, and then some extension and applications. Okay, so the question which was asked in the original paper, this is not going to be what's happening with this, is whether there is a universal description of the growth of an interface, and universality here is in the same sense as in critical phenomena, meaning that you are looking for a large-scale coarse-grained model to describe growth of interface. So let's start with one dimension. I will focus on one dimension, and let's just look at some grains which are falling randomly on some surface. And I'm going to look at the growth of the height field. And in particular, so it's growing linearly in time, and it has fluctuations, and I'm interested in the fluctuations. So if the model is just that, then the equation is just linear growth plus some noise. And if there is some redistribution locally of grains, then you will have an additional term, which is this Laplacian term, and that's the Edouard-Wilkinson equation for growth. It's the simplest one. It is a linear stochastic equation, so it can be solved explicitly. And if you do that, you find that the height fluctuation grow like distance to the power 1/2. The dynamics is diffusive, and the height grow as a function of time, the height fluctuations as t to the power 1/4. So this is the Edouard-Wilkinson scaling. And the distribution is Gaussian, and it's a very simple model. It actually describes an equilibrium situation because the equation can be written in some detailed balance form like this, and it converges to some Gibbs equilibrium. So this equation actually describes equilibrium growth if you want. For instance, if you have an interface in the Ising model in global dynamics in the Ising model without external field, it's a little bit too simple. So we want something where there is irreversibility in the growth. And people at the time looked, for instance, at model of ballistic deposition where the growth can actually, the grain can actually stick. Here, for instance, or the Eden model, where all perimeter sites are equally likely. And in all these models, there are additional phenomenon, which is lateral growth. You can also think of a growth process which grows normal to the interface. And this is what this drawing was in a paper of KPZ paper. So if you have an interface which grows with some fixed velocity along its normal, and if the interface is tilted, if it has a gradient, then if you project on the vertical direction, you have this cosine factor. So you have this nonlinear term if you expand. And this is what one way to see the KPZ equation. Okay, I'm going to, of course, there is a mean velocity for the growth, but I'm going to go to the moving frame all the time, so this additional term here will not be there. Now, I will discuss now that this nonlinear term is actually irrelevant, so it leads to a new universality class with these exponents in one dimension. So let me discuss that now. So, so that was one way of justifying the KPZ equation, is to say, for instance, if the rate of growth depends on the slope of the interface, then you would have this nonlinear term. But there's a more general way of thinking about it, which is just to say that we can write the, starting from the Edouard-Wilkinson equation, we write all the terms which are allowed by symmetry. And you see, if you have growth, the H2 minus H symmetry is broken. So it means that you are authorized to have such a term. And then you can see that this term is actually relevant because you can do power counting around the Edouard-Wilkinson fixed point. So at the Edouard-Wilkinson fixed point, the height fluctuation are like x distance to power 1/2. So you see that in this, if you compare these two terms, they have the same number of gradients, but there's an additional power of height of h. So this term is more relevant than this term. And it means that it will lead to different universality class. You can also see, for instance, that higher order nonlinearities are less relevant by just the same power counting. So you need only this term. And this is what led to this to the KPZ equation. So this will describe growth, non-equilibrium dynamics, because it's not, you cannot write it as a derivative of some Hamiltonian. So there is no really energy functional that you can write. So it will describe something irreversible, like the growth of a stable phase into an unstable one. Okay, so some property of the KPZ equation. The first property, which was emphasized in a KPZ paper, is a relation to the Burgers equation. If you define a velocity field, which is the gradient of the height of KPZ, then it satisfies, you take derivative of KPZ equation, you see that it satisfies this equation, which is nothing but the Burgers equation. So it's some kind of simplification of the Navier-Stokes equation with some conservative noise. And this was studied a few years before by Foster, Nelson, and Stephen in a famous paper, where they did, actually they did Navier-Stokes, but they also have a few paragraphs on Burgers, very concise ones, but and they do a dynamical RG, and they pointed out about exact exponent in one dimension because there are two symmetries. So this was developed further in a KPZ paper. And what are these two symmetries? So the two symmetries, the first one is Galilean invariance, which you would expect in fluid mechanics, which is in Burgers, which is this transformation. So it's if you do this transformation in KPZ equation, you get essentially the same KPZ equation. Okay, I wrote some details here, but it's not so important. It's also called a statistical tilt symmetry. So if this transform field, if you write this H tilde, where you have this transformation on H, and if H is a solution, and H tilde is also a solution, but with a tilted noise. But you can see that if the noise is white in time, so you have delta function in time, then the tilted noise and the original noise have the same correlation. So statistically, you can see that the new transform height has the same property. This leads to this relation in rho, which relates the distribution of probability of H at some point and at another point. And it leads to this, by just identifying the dimension of these terms, it leads to this important universal scaling relation between the two exponents. So there are two exponents, height as a function of x, which they call chi, and the dynamical exponent, which is called z. And there is this universal relation between them, which is valid in any dimension. This Galilean variance is valid in any dimension. Now, what's peculiar about one dimension is that there is another symmetry, which is that the stationary measure of the KPZ equation is Brownian. In other words, if you start with this probability distribution of the field, it will remain like this for all time. And this will actually implies another relation of exponents, so it gives you these scaling exponents. It is interesting to note that at the same time, roughly at the same time, there was some work by Spohn and collaborators which looked at lattice gas model, where you have conserved density field, and where the current is some nonlinear function of the density, and you take into account diffusion and noise, and you get the same exponents. So it's some kind of generalized Burger's equation, if you want. Okay, so these are the exponents for one dimension. Now, what is the other important property of the KPZ equation? The other property, which is really beautiful, is the connection to directed polymers, which is a problem with quench disorder. So you start from the KPZ equation, you define a partition sum Z, which is exponential of the height field. And then you see that this function Z will satisfy the linear equation. So in some sense, you can linearize the KPZ equation with this so-called Kolov transformation. But the additive noise now becomes multiplicative noise. So eta here is a KPZ noise. This V is, I'm going to interpret it now as a random potential. They are essentially equal. And this is called the stochastic heat equation. It's multiplicative noise. It's linear equation. And if you recall quantum mechanics, you can think of this as some kind of wave function equation, Schrödinger equation in imaginary time. So you can see that it describes directed trajectories, directed paths in 1+1 dimension. So this would be a path integral representation of the solution for this type of initial condition. And it corresponds to the partition sum of continuum directed polymer in 1+1 dimension. Now, this continuum directed polymer representation of the solution of the stochastic heat equation actually correspond to a finite temperature situation. So you can see there is a temperature factor here. So it's finite temperature polymer. It's a canonical statistical mechanics problem in presence of random potential. And now you can see that there is super diffusion of the polymer. The polymer wants to explore favorable configuration of the disorder. So that gives this 2/3 exponent. And this is a finite temperature representation. But if now you go to very long polymers, you can see that actually they are localized very close to the optimal path. And it corresponds to some kind of zero temperature fixed points, as I will discuss very soon. Now, this mapping to directed polymer is valid in any dimension. So the KPZ equation in dimension D can be represented by a directed polymer problem in dimension D+1. And it's a very powerful mapping. Now, what about experiments? So I think the most impressive experiment is the one by Takeuchi and Sano on liquid crystal in two-dimensional geometry. So what they have is two-dimensional geometry. They can nucleate a stable phase. So there are two phases of turbulent liquid crystal, and they can nucleate by shining a laser a stable phase inside an unstable phase. So you see that the droplet now is growing. This is color is called is time. And they can, their experiment is very nice because they can do essentially any initial condition they want. For instance, they can shine the laser at the center, or they can shine the laser along a line. So in that case, you have a flat initial condition, and this is called a droplet initial condition. And they observe the 1/3 exponent, and they observe much more, as I will show later. And these exponents have been also observed in a number of experiments. Actually, recently, they have been observed also in condensed matter physics. But you can ask, if you look at the dates of these papers, you can ask, why did it take so long to observe the KPZ exponents, since KPZ is supposed to be so ubiquitous, right? And the reason is that it's actually not so easy to avoid quench disorder effect or long-range effect in experiments. And the beauty of this experiment of Takeuchi and Sano is that they use turbulent liquid crystals so that all effects of disorder are completely washed out. And they can have also very, very big statistics. Okay, so let me now briefly mention KPZ equation in higher dimension. Well, one can do power counting at the Gaussian fixed point, the equivalent of the Edward-Wilkinson fixed point. And one can see that the nonlinear term now is relevant for d smaller than 2. So d equal 2 appears as a critical dimension. And what was found in the KPZ paper by defining some dimensionless coupling is some renormalization group equation for this nonlinearity. And they found that in less than 2 dimension or in 2 dimension, there is a flow of this nonlinear coupling to large values. So it's non-perturbative regime. But in more than 2 dimension, there is an intermediate, so epsilon negative. There's an intermediate fixed point which separates a weak noise phase where the nonlinearity is irrelevant, and a strong noise phase. So there is a bifurcation in 2 dimension, but it's only the appearance of a phase where weak noise phase, high temperature phase for the directed polymer. It doesn't tell you much, this RG, about this strong noise KPZ fixed point, which is supposed to be there, and it's observed, of course, in numerical simulation of, for instance, the directed polymer. You can, as I mentioned in previous slides, it's easy by doing transform matrix simulation to see that directed paths in random potential localize and that they are controlled by 0 temperature fixed point. This means infinite G fixed point if you want. And okay, so people have looked a lot in this directed polymer picture to this fixed point. And in terms of directed polymer, this growth exponent for the height is actually exactly related to an exponent which describes the fluctuation of the energy of the optimal path from sample to sample. Okay, so in 2 dimension, there is very little known actually, besides numerical simulations. So there was a conjecture by Kim and Kosterlitz that this exponent takes this value, but was based on numerics. And more recent numerics show that it's not certainly not exact, although it's not such a bad approximation in 2 dimensions, but it's not exact. I just want to point out this paper about stationary 2D KPZ, where they made a very nice study of what can be conformally invariant and what cannot be conformally invariant. But okay. Now, the only limit in which there is really analytic results is the large D limit. First, with this exact solution of Derrida and Spohn for directed polymer on the Cayley tree. And then this very beautiful paper by Mézard and Parisi, where they consider the variational ansatz, which becomes exact in a large dimension limit, with replica to describe the Gibbs measure, when the measure for the directed polymers. And this is an extension. Okay, so both of these methods give insight in large dimension limit, and they both lead to the same conclusion that there is a glass phase, meaning this low temperature phase, with one-step replica symmetry breaking in that limit. And what is not known is what is the upper critical dimension? Is there a critical dimension above which one recovers this mean field theory or not? So I think this is still an open problem, although the experts about this are actually here. But okay, I'm curious to know what the current status is, but to my knowledge, it's not fixed. Okay, so now let's get to random matrix theory. A priori, completely unrelated subject, but it will come out to be related, as we will see. So let's consider large random matrices with independent random entries. And as probably you know, there are three classical ensembles of random matrices. The first one is when the random matrix is symmetric, real symmetric. Its probability measure then satisfies a symmetry under the orthogonal group. And this is called the Gaussian orthogonal ensemble. The other one is called the Gaussian unitary ensemble for Hermitian matrices. And then there is also the Gaussian symplectic ensemble. So these three ensembles of random matrix, if you look at their eigenvalues, they are random eigenvalues, but they all fall on a semicircle spectrum at large for large matrices. And there is explicit formula since Wigner and Dyson for the joint distribution of their eigenvalue. It involves this van der Monde determinant to the power beta. So beta is a Dyson index. It's 1 for GOE, 2 for GOE, 4 for GSE. Okay, so what I will be interested in here is what happens near the edge of the spectrum. So what is the largest eigenvalue? And it was found that the distribution of the largest eigenvalue by Tracy and Widom. So the largest eigenvalue, here I've rescaled the matrix so that the edge is at 2n. And then if I do that, then the fluctuation of this largest eigenvalue are scale like n to the 1/3. And this 1/3 will be actually the same as a KPZ 1/3, as we're going to see, with a random variable here, which has the so-called Tracy-Widom distribution. And to describe them, I will need to now get a bit more into the structure of this probability measure for the eigenvalues. So this so-called determinantal point process. So let me again concentrate on the Gaussian unitary ensemble, which has this distribution of eigenvalues. Then it is possible to write this van der Monde determinant as a determinant with using Hermite polynomials. So in fact, I can rewrite this measure on the eigenvalues using the eigenstates of the harmonic oscillator, elementary quantum mechanics. And in fact, this is can be written, since it's a van der Monde square, as a square of the determinant of the n lowest eigenfunctions of the harmonic oscillators. So if you remember quantum mechanics of non-interacting fermions, this is exactly the ground state of n non-interacting fermions. And it's interesting to actually, you know that product of determinants are determinants of products of matrix. So you can rewrite it as a single determinant in terms of this object, which is called a kernel, which is basically a projector, a projection operator on the n lowest eigenfunctions of the harmonic oscillator. Okay, so why am I talking about this object? Well, it turns out that determinantal point process have the property that any marginal distribution of eigenvalue, so if I integrate over all the eigenvalue except small n of them, then the probability is still a determinant, but small n by small n. So that defines what mathematicians call determinantal point process. And the GUE distribution of eigenvalue is a determinantal point process. And now there is a very nice property of determinantal point process, which is that it's possible to compute, for instance, the probability that there is no particle in some ensemble, is in some interval J, and is given by this object, which is a Freedom determinant. So it's a determinant in functional space. I will explain a bit later. So what is this kernel here? Kg is a projection of this kernel on the interval that you are interested in. So then if we want to know the cumulative distribution of the maximum eigenvalue, it means that it's the same as the probability that the interval lambda to infinity is empty. So it can be expressed as a Freedom determinant like this. Okay, so this is getting to a formula that Tracy and Widom got. So what is the Freedom determinant? Well, it's a determinant of a linear operator acting on functions. You can write it like this, or you can also write it as a sum like this, and it will come out later in the talk. And it's actually very easy to compute on with Mathematica. It's a few lines of codes, and there's a very nice paper by Bornemann, which explains how to do these approximations by finite matrices, finite determinants, and shows that there are exponential convergence. In fact, actually, this Tracy-Widom distribution now, I think, are built in Mathematica. So this, I mean, the conclusion is that these Freedom determinants are very easy to compute numerically. And what Tracy and Widom found is that the distribution of largest eigenvalue for the GUE is given by this Freedom determinant with this Airy kernel. Why is it the Airy kernel? Well, because you are looking at the edge of an harmonic oscillator. Okay, so it's you can linearize basically, and you get Airy functions. So this is a formula of Tracy-Widom, and they also show that it obeys. It can be also expressed in terms of solution of Penrose equations. Now, these functions, Tracy-Widom distribution, have universal cubic tails on the left and 3½ power tails on the right. And they are very different from Gamble distribution, which are distribution of maximum of uncorrelated random variables. That means the eigenvalue of GUE are very correlated. Okay, so this is, we're going to need this, and there is a similar formula for the GOE ensemble. Okay, so let me now quickly, what time is this going to stop?
You see that time.
Yeah, I do, but I'm also at the beginning of the talk. So
Already spent half an hour.
Half an hour? Okay, good. So I have to accelerate. Okay, so first KPZ, second KPZ revolution, which I'm now going to explain, which is the solution of models which are called determinantal, in the sense that the transition probability can all express as determinants, and they can be solved, and the high distribution can be computed, and there are connections to random matrix theory and to random partitions. Okay, so the revolution started with this solution of the Ulam's problem. What is Ulam's problem? Well, you take a random permutation. So here it's a permutation of 10 elements. And you ask, about the longest increasing subsequence in this permutation. So you see that the longest increasing subsequence here is this 1, 3, 4, and then 6, 9. So it's length 5. So now it's a combinatorial problem of interest for mathematicians, certainly. What is the distribution of lengths of the longest increasing subsequence for large permutations, large random permutations? So Bike, Dive, and Johansson showed that at large n, for large permutation, it grows like square root of n plus some fluctuations. And those fluctuations are precisely a Tracy-Widom distribution associated to the GW ensemble. So this is based on a quite amazing formula, which gives probability of this length in terms of a matrix integral. This formula was actually known before by Diaconis and so on. So they did the asymptotic of this formula, basically. But they didn't, I think they didn't know that Gross and Witten had already studied that. I mean, they didn't have this formula, but they studied the right-hand side here. And Perivalshevitz actually showed that it has a connection to Palmway equation and so on. So there was already some work in high energy physics about this matrix integral. Now, why is it interesting? Why is it relevant for KPZ? Well, it turns out that it can be mapped, this problem can be mapped to statistics of the optimal energy of a directed polymer in a random potential. It's not totally obvious at first sight, but it goes like this. Suppose I'm going to throw in this square, I'm going to throw randomly points. So Poisson points. Here I've taken a sample of 10 points. Now I can put labels for the coordinate of these points along this axis and this axis. And it turns out that this defines a permutation. So for instance, the 1 here is associated to 8. So this is the first number here, and so on. So for each configuration of point, there is a permutation. And now the nice thing is that if you look at the longest increasing subsequence, it exactly maps to the optimal path which goes up and collects a maximum number of points. So it's really a directed polymer problem. And the result of Bike, Johansson, Deift shows that the optimal energy has Tracy-Widom fluctuations. Okay, so this was a very important result. And quite related result was obtained by Hofer and Spohn by considering this model of growth now, where you have particles falling on the surface, and when they reach the surface, they form terraces like this, which move with uniform velocity. And when the terraces meet, then they annihilate. So this is a growth process, which is nothing but the growth of an Ising interface in presence of an external field. And just some mapping of the previous problem to this problem leads again to a Tracy-Widom distribution for the fluctuation of the height of this process. Then there is another model which is closely related, which is a totally asymmetric exclusion process, where you have now, it's a transport, it's a model of transport of particle in one dimension. So you have particle on this line, and they move randomly at random times to the right, only to the right, only if the site is not occupied. So you can actually define, for each configuration of particles, you can define a height by just saying that if there is a particle, the height goes up. If there is no particle, it goes down. So it maps to a random surface. And this dynamics of the particle is equivalent to growth of this surface. So what was shown by Johansson for this model is that if you put initial condition where all particles are on the right, so the initial height is this wedge, then the particle will start jumping to the right, the initial particle on the left, they will start jumping to the right, and the profile will relax, and the fluctuation, again, are described by Tracy-Widom distribution. Okay, so then there is another model of directed polymer on the square lattice, which I'm not going to get into, which is also similar result. Okay, very nice. So now what about space point height correlations? So I've shown you the distribution at one point. What is about the distribution of height of the KPZ in this KPZ class model at different points? And now it's interesting because now it's actually involves, again, random matrices, but matrix Brownian motions. Okay, so now you're going to introduce a fictitious time, and you have to have a random matrix which will evolve in time according to this equation. So this is matrix white noise. So if you want, you have a random matrix which each element performs Brownian motion. In fact, in this form, it's actually more like Ornstein-Uhlenbeck process. And we are going to be interested in the largest eigenvalue, again, of this random matrix. And the eigenvalue of this random matrix is what's called perform what's called a Dyson-Brownian motion, which is a collection of they have a collection of non-intersecting trajectories, and you are interested in the top line. Okay, now why is this going to come out? I will tell you, but this is what we're going to need. And it was shown by Pfeiffer and Spohn that if you zoom on the top line and the right scale, that defines a process which is called the Airy process. So if you look at the statistics of this largest eigenvalue as a function of this fictitious time, and if you rescale by n to the 2/3, the size of the matrix, then you get a process which is stationary, and it's called the Airy process. And it has some nice property because the set of all eigenvalues here in the Dyson-Brownian motion has a determinantal structure again. So I won't get too much into the detail, but there's a formula for the joint distribution of a different fictitious time for this process in terms, again, of determinant of some extended kernel. Okay, so what Pfeiffer, Spohn, Johansson showed is that if you now take the PNG model, so the PNG interface is a top line here in this drawing. If you look at it at very large time, and if you rescale time and space, if you rescale, sorry, the height and the space in this way, then this converges to the Airy process minus a parabola. So what it's telling you really is that if you look at this KPZ interface, you can see it essentially as a top curve of non-crossing Brownians. And this is basically telling you what the multi-point correlations are, and there's explicit formula. Okay, so this extends to the other type of initial condition, which involve GOE ensemble, and I'm going to finish with this. I mean, not finish, but I will talk now about this stationary case, which is a bike-Rains case. Okay, so now let's talk about stationary KPZ. So it looks again a bit unrelated, but the important work was done by Bike and Rains, where they again looked at this Poisson point, but now they put also Poisson point on the boundaries with a different rate. And if this rate is chosen equal to some critical value, then there is some interesting distribution which emerge, which they have explicit formula in terms of solution of Painlevé equation again. And it turns out, this was shown by Pfeiffer and Spohn, that if you look again at this PNG model of growth with stationary initial condition, then you get at large time exactly this bike-Rains distribution. Okay, and in this paper, actually, Pfeiffer and Spohn did much more because they actually also computed the space-time correlation of the height, which is expressed, for instance, here in terms of the Burger's field, or the derivative of the height. They obtained this formula for stationary KPZ. And this is a universal function. And we are going to see later that it appears in a number of cases. Okay, so now I think I will move to the next step. Again, how much time do I have left? 15? Okay, so back to KPZ equation. In particular, where does the KPZ equation stand in this KPZ class? So by KPZ equation, from now on, I'm going to talk about D=1, space-time white noise, and solutions for all times. So for short time, one can actually see that this nonlinear term is not important. So you get just Edward Wilkinson. And eventually, when time increases, it becomes more and more important, and you're supposed to reach KPZ fixed point. But the question is, how do you reach it? Is the KPZ equation itself in a KPZ class? And what does the KPZ equation at finite time describe? To answer the last question, let me just briefly mention some extension of this extrusion process, which is the asymmetric extrusion process, where now the particle can jump to the right or the left. And it was proved that if you choose now a weak asymmetry and you rescale space and time, then the height of this model converges to the KPZ equation at finite time. Similarly, if you take a directed polymer on a lattice and you take high temperature limit, it also converges to KPZ equation at finite time. So there is this kind of graph of diagram where you can see that the finite time KPZ equation is an interpolation between the Edward Wilkinson fixed point and the strong KPZ fixed point. The KPZ fixed point attracts all the models in the KPZ class, and that's called strong universality. But if you take some of these models, like this asymmetric exclusion or lattice-directed polymer at high temperature, you can scale them to the KPZ equation. And that's called weak universality. Okay, so now it's possible to solve the KPZ equation using replica. And the method is so-called replica Bethe-Ansatz. Now, what is the idea? You start from KPZ equation. You're going to use this Koloff mapping to map it onto continuum-directed polymers in a random potential. And then you're going to use replica to study that problem and to map it to a problem of quantum mechanics of bosons in one dimension. So this is so-called delta Bose gas, which can be solved using the Bethe-Ansatz. So this was pioneered by Kardar, and there were questions now about how do you extract from it the distribution of the height for KPZ equation. And this was done only in 2010. And I will explain briefly how. Okay, so, okay, this I don't need so much. This I don't need too much either. Okay, so let me concentrate on the problem of polymer with fixed endpoints, which corresponds to initial condition in KPZ, which is very localized, which is called a narrow wedge, which in fact is also, as can be shown, represented by the droplet. I mean, it's also called droplet initial condition or curved geometry initial condition. Okay, so we're going to compute the integer moments of the partition sum, and from them we're going to try to get the distribution of the height. It's totally illegal because this is going to be a case where the moments are growing much, much too fast, but we're still going to do it. Going to close the eyes and do it. Don't listen to mathematicians, just do it. Okay, so you can you can consider moments of partition sums with different points, and they satisfy an evolution equation which involves the Hamiltonian of quantum particles. I mean, the idea is very simple. If you have two directed polymers in the same random potential, then when you average over disorder, it will generate some attraction between them. So you can relate this type of correlation to expectation value in quantum mechanics of this evolution operator in imaginary time. Okay, so once you know that, well, you can write this formula, and then what do you need to compute it? You need the eigenstates of H, and you need the eigen energy, and you get this type of formula. You need only bosons because the initial and final states here are just symmetric. And for this model, the eigenstates are known. They are given by superposition of plane waves with some phase factor. This is better on that. And they are indexed by a set of rapidities, which are solution of beta equation, but we're not going to need them. Okay, so we have n bosons with attraction. So clearly this will lead to bound states. And in fact, the ground state has a very simple structure. It's just a bound state of n replica. And it has this energy, this binding energy. So Carda in 87 concluded from that the nth integral moment of the partition sum will grow like this, exponential n cubed t, which is a very fast growth. So from this, you can see the exponent 1/3, but you cannot really continue this formula in n, actually, because you have already taken infinite space, infinite time, so it's too much. However, you can relate it to the tail of the Tracy-Widom distribution. I won't get into the detail. So if you really want the distribution, you need to sum over all the eigenstates, which looks at first sight a bit formidable, but in fact, they have a simple structure. All the eigenstates are just obtained by partitioning the n particles into subsets, which are bound states, which are called strings. And the total energy is simply the sum of the kinetic energy of the strings plus binding energy. So something's happening with the unstable. Okay, so if you want to evaluate now this sum, this factor here is very simple. It's just purely factorial n, but the difficult part is the norm of these eigenstates. But it was actually found obtained in 2007 by Calabrese and co, and it has this form. So the norm of the eigenstates being known, then it's relatively easy to write exact formula for the moment, which takes this type of form. I won't get into too much detail. It's a bunch of integrals. And the question is, how do you continue this? Either you continue this to n equals 0, or what do you do with this? Okay, so one way to do something with this is to introduce a generating function, which is summing over n, and introducing, okay, I'm going to call lambda the time to the power 1/3, because I know this is going to be the scale of the fluctuation. So we introduce this generating function, which is actually a generating function which was already introduced by Derrida and Spohn in a solution of the Cayley-tree problem. And it has a nice property that if lambda goes to infinity, it's a double exponential, so it gives you the cumulative distribution of the free energy. If you know how to calculate this function for arbitrary lambda, you take lambda to infinity and you get the cumulative distribution. Okay, I'm sorry, I have to go a bit fast, but just to give you an idea, then now you are summing over n, so you can reorganize all your sums, and you end up with this type of formula where now you sum over the number of strings, the number of excited state of bound states. And in this formula, you see that there is summation over m with a very fast growing factor here, exponential m cubed. So it's very scary because it's not at all a convergence series. But we are physicists, so we're going to use this trick, which converts exponential w cube into a linear exponential, so-called Airy trick. So that allows you to obtain now a series which is geometric. So we know how to resum them. And now this factor still looks nasty, but in fact, you can see that it's actually a determinant. So we have a determinant. So now we can just do some manipulations, and we end up with a representation which is, again, a determinant of some kernel where there is this Airy function, which I introduced. And then there is this geometric series, which gives me this kind of Fermi factor looking term. And what I show you here is a generating function has exactly the form of a Fredholm determinant, which I showed in previous slides. So the conclusion is that this generating function is a Fredholm determinant for arbitrary time. of some well-defined kernel, and then I can take the large time limit and recover the Tracy-Widom distribution. Okay, how much time? 5 minutes. Okay, so now I'm going to make some choices. So we have also a solution for flat. I want to show, just point out that there is also a solution for the stationary, using replicas for the stationary case by Imamura and Sasamoto. We recover the bicranes by similar methods. So it's possible to extract the distribution of height at arbitrary time. There were these works by mathematicians who put this on some rigorous basis. Except the flat case. The flat case is still not been proved by mathematicians. The other two cases have been proved. Okay, so now what is beautiful is that this actually can be seen in the experiments. So in this experiment of Takeuchi's Shano, and they have enough statistics to determine the kurtosis and skewness and show that it agrees with the prediction. And they have also this comparison with the correlation of the height at different points, the Seri process. So there are beautiful realization, and they also recently managed to find the bicranes distribution by, again, they are preparing the interface in some Brownian kind of configuration with their laser, and they are able to find the bicranes distribution and show it in the experiment. Okay, so this is more math, and I'm going to go very fast. So just one, I could not give this talk without mentioning, of course, the Fields Medal of Hairer, who did, let's say, ultraviolet KPZ, so giving a meaning, mathematical meaning. So it's some kind of renormalization, UV renormalization of the KPZ equation, but directly on the stochastic PDE. And it applies to many other stochastic PDE. So that's a beautiful work, but I would not be even able to explain to you how it works. It's I was explaining it several times, but I still do not really understand it very well. Okay, what is closer to what I told you is progress on stochastic integrability. So for instance, these people, these mathematicians found a formula for the what they call the KPZ fixed point, basically arbitrary initial condition. Then there was development in mathematics about McDonald process and higher spin stochastic vertex model. So it's a full field of models which is called integrable probability, where they made this replica method rigorous, but they did much more than that. So I'm going to I cannot explain this, I don't have time. This is this general formula for the kernel for arbitrary initial condition. It satisfies some nonlinear equation for arbitrary initial condition. Okay, so this I will pass, and this is the kind of pile of models and mathematical structure which arose in recent years. And for instance, the KPZ equation is hidden somewhere here, directed polymer and the hierarchies. Okay, but you see that all of these things are just can be obtained from this McDonald process. Okay, so this is piles of models which go into KPZ equation. These two times I think I will skip, although it's very nice, but just to show that there is some persistent memory in KPZ. If you look at KPZ at two different times now, and if you look at this droplet geometry, you can actually compute the correlation between this covariance ratio at two different times and see that there is explicitly that there is memory for this type of geometry, and it has something to do with the overlap of directed polymers. How much time? 1 minute, okay. Okay, so in 1 minute, a few applications. So there is I will just scan the transparency. So there is application to distribution of conductance in localized phase of, in Anderson localized phase, which is found to be also given by Tracy-Widom distributions. This corresponds to directed polymer with non-positive weights. Then there is this beautiful paper by Adam Nahum and collaborators, which found KPZ that the entanglement, the growth of entanglement entropy in presence of noise in this random circuit model is given by KPZ fluctuations. Obviously, I don't have time to discuss it. Okay, so then there is a quench KPZ equation, which is also something very interesting. I don't have time to discuss it. I will just mention the coupled KPZ equation, which started with the Ertats and Kardar paper. So they asked about a directed line, which is driven on some substrate. In that case, you have two fluctuation direction, perpendicular to motion or parallel to motion, and you have this couple is described by these coupled KPZ equations. And this happens, okay, this also describes moving vortex lattices and so on. And more recently, this coupled KPZ equation appeared in what's called nonlinear fluctuating hydrodynamics, which describes, for instance, Fermi-Pascal anharmonic chain at mesoscopic scales. So this is work by Spohn and collaborators, which show that this type of system are described by a coupled KPZ equation, and that there are some, again, this universal function appearing. There's some even more crazy results with dynamical exponents given by ratio of Fibonacci numbers. But I don't have time to talk about it. So I just want to spend a little bit of time on this one because it's still open question, actually, which is it was discovered that if you take a quantum Heisenberg chain at high temperature and you look at the spin transport, so this is the XXZ model. If you change this parameter delta, you can go from ballistic phase to diffusive phase. And at delta equal 1, you have SU2 symmetry, you have integrability. And it was discovered by Prosen and collaborators that the 2-point spin correlation, 2-time spin correlation, is actually takes actually the KPZ form. This was an empirical observation from numerics. And people are actively trying to understand where it's coming from. Because there is no, it's an equilibrium system, it's infinite temperature. And there is no noise, there is no noise, yes. It's a quantum system at high temperature. So there is some argument which, based on Magnon bound states, which actually can justify this 2/3 exponent. And people have tried to model the system by a single KPZ equation, but that actually description has failed. But more recently, they realized that one actually needs two modes of KPZ to describe the system. It's still empirical, but I mean there is some derivation of these coefficients, but it's still relatively phenomenological. But there's some calculation behind. And you see that this is, I mean, they notice that this is very similar to the Ertats-Kardar coupled equation, which Ertats and Kardar actually argued to give also the KPZ exponent, dynamical exponent. So that could be maybe an explanation for this problem. Okay, so let me just finish with this open questions. And okay, how much time I have? Negative now?
Yes.
Okay, so then I will go to the cake. So this is the famous 30 years anniversary, which the cake was done at the KITP program in 2016. And now the 40th birthday is coming, and we all hope that there will be another cake and another KITP program maybe. And I'm going to stop there.
Okay, thanks, Pierre. Comments, question? George, you want to add some?
Well, Pierre, it's quite impressive there's so many different evolutions in which you can start from one question, you can go to very different regions, and especially in mathematics, where one would never suspected these things, and also the fact that one could get a field medal for studying these things. One thing that impressed me in your talk that I was not aware of was that there's one way to formulate, to define some conformal invariant observable in KPZ, because you mentioned that KPZ, there's some kind of conformal invariance.
Well, I mentioned a paper in 2 dimensions.
Yes.
Yeah, so they define, so there was some conjecture that the contour lines of a KPZ interface in 2 dimensions was, well, these contour lines were conformal invariant. So in this paper, they showed that it's not.
Okay.
Okay, but stop. But they managed to find one ensemble of lines which is conformal invariant. So I think you should read the paper and make your opinion. I mean,
okay, but
it's an interesting paper, but I don't know what I mean, I don't think they actually even know themselves what the significance of it is, but
okay,
it's an observation, which is interesting, but.
Okay, thank you. No, because it would be interesting if one could define conformal invariant correlation functions.
Yeah.
Okay, so anyhow, thank you. To you.
Thanks, George. Any other question, comment? If not, I would like to ask you just to go one slide back, because my question was about, so you show so many nice results that it seems that you understood everything. No, the open question slide.
Ah, yeah, okay, yes.
Because my question was, what is still to be understood, given that you present us really a cornucopia of results, impressive.
Yeah, in 1 dimension, there are many things which have been done, so, but there are still some things to be done in, I mean, here it's more like mathematical questions. I mean, it's not, you know, I'm
From the physical point of view, do you think that most is understood?
Okay,
for example, I remember that people were discussing the upper critical dimension of this.
Yeah, so in more than 1 dimension, I would say essentially enough. I mean, very little is known. So yes, we certainly need progress there. I mean,
so mathematicians will work in the and physicists should
more than 1 dimension, but they are having a hard time. I mean, I think they proved the existence of the high temperature phase. Okay. But they to get to the KPZ fixed point, it's not.
And the couple KPZ equation,
yes.
Is the example you show us. So
yeah, there are these results which usually are the case where the modes velocity are different, but when the modes velocity are all the same, I think it's still open. But okay.
Thanks. There are no more questions. We thanks Pierre again.